Good morning. My name is Syed Akbar Ali Salman, roll number 4003 from Triple E Department, third year. My topic name is switch reluctance motor. Now, switch reluctance motor. Introduction of switch reluctance motor. The switch reluctance motor is known as in short form SRM is an electrical motor in which torque is produced by the tendency of its movable part to move to a position where the inductance of the excited winding is maximized. SRM is a type of synchronous machine. It has wound field coils of a DC motor for its stator winding and has no coils or magnets on its rotor. It can be seen that both the stator and rotor have silent poles, hence the machine is a doubly silent, singly excited machine. Now here, introduction on stator winding on diametrically opposite poles are connected in series or parallel to form one phase of the motor. Several combinations of stator and rotor poles are possible, such as 6x4, 6 stator poles and 4 rotor poles, 8x4, 10x6, etc. The configuration with higher number of stator rotor pole combination. Here 6x4 pole and 6x6 poles, 8x6 poles, sorry. Now we can see in this diagrams here 6x4 poles are also there available and 8x6 poles also there available. Now configuration. Initial classification is made on the basis of the nature of the motion, that is rotating of linear. The linear SRM LSRM have found application in the marketplace by catering to machine tool servos. The rotatory machine based SRM is differentiated to radial field SRM and axial field SRM by the nature of the magnetic field path as to its directional with respect to the axial length of the machine. Here is the flowchart which shows SRM. It have two parts, rotary SRM, linear SRM, and from radial field, rotary SRM, radial field and axial field. From radial field we have two differentiation. Long flux path machines, doubly silent with concentric winding, diametrically opposite winding are in series to form a phase, and the other one is short flux path machine, adjacent pole winding are in series to form a phase winding. Whereas we talk about axial field, it has two types, single stack, multi stack. Now configuration code, radial field SRM, which shows in a figure, it looks something like this. The magnetic field path is perpendicular to the shaft or along the radius of the cylindrical stator and rotor. Short flux path in a 5-phase radial field SRM with 10x8 poles. Configuration code, axial field SRM, the magnetic field path is along the axial direction. Whole motor is look like this, rotor is located like this, the short magnetic flux path is located like this. As we see on this page, three types of parts of a motor. Now LSRM, the motion of the motor is linear structure. A LSRM may have winding either on the stator or translator. The moving part, fixed part is called track, moving part is called translator. Application, ideal for machine tool drives. Now we can see in this figure, one side LSRM, Here we can see that T1, T2, T3, T4, T5, T6 are connected to the switch S1, S2, S3, S4, S5, S6, S7, S8, S9, and in the right hand side stator and transmitter is placed. Now two-side LSRM with winding on the translators. Principle of operation: cross-sectional model of a three-phase SRM winding arrangements and equilibrium position with phase 1 excited. Principle of operating cont: rotor rotation as switching sequence proceeds in a three-phase SRM. The rotation direction is opposition to the direction of the excited phase. The switching angle for the phase current is controlled and synchronized with the rotor position, usually by means of a shaft position sensor. Torque production, flux linkage. Now here we can see that a graph of a torque production. The y-axis is known as flux linkage and the x-axis is known as current I. Here from 0 to some value the core energy available, and from some value to top stored field energy, and the curve side is known as magnetization curve. Here definition of co-energy and short field energy. The torque production in SRM can be explained using the eliminatory principle of electromechanical energy conversion. The general expression for the torque produced by one phase at any rotor position is T is equals to dou W by dou theta to the base I is equals to constant, where T is the torque, W is the co-energy, delta theta is the displacement of the rotor. The constant current constraint in the formula ensures that during such a displacement the mechanical work done is exactly equal to the change in the co-energy. Torque production in a motor with no magnetic saturation, the magnetization curve would be straight lines. At any position, the co-energy and the stored magnetic energy are equal, which are given by Wf is equals to W, which is equals to 1 by 2 Li whole square, where L is the inductance of a exciting stator phase at a particular position. In this case, the instantaneous torque can be derived as T is equals to half I square dl by d theta. Energy conversion process in the real switch reluctance motor. The energy conversion process in an SRM can be evaluated using the power balance relationship. Here we can see the formula, which is written as P input, P to the base input is equals to I square to the base phase R to the base S plus d by dt bracket 1 by 2 L to the base phase I square to the base phase whole bracket plus half I square to the base phase dl to the base phase by d theta. The first term represents the stator winding losses and the second term denotes the rate of change of magnetic stored energy. The third term is the mechanical output power. The second term always exceeds the third term. The most effective use of the energy supplied is to maintain phase current constant during the positive dl phase by d theta slope, in which way the second term is equal to 0. Torque production. The torque is proportional to the square of the current, and hence the current can be unipolar to produce unidirectional torque. Since the torque is proportional to the square of the current, it has a good starting torque. Because the stator inductance is non-linear, A simple equivalent circuit development for SRM is not possible. The torque characteristics of SRM are dependent on the relationship between flux linkage and rotor position as a function of current. Here we can see that equivalent circuit, which represents an elementary equivalent circuit for the SRM, can be derived neglecting the mutual inductance between the phase as following. Here is some formulas. The first term is the resistive voltage drop, the second term is the inductive voltage drop, and the third one is the induced EMF, which can be very high at high speed. Torque speed characteristics. The graph shows torque speed characteristics from y-axis torque per unit and from right axis rotor speed per unit. Here we can see the graph from 0 to WB limit region constant torque, which is known as W1, and from there to WP constant power limit region, which is known as W2. From W2 to W3 constant power speed limit region, which is known as W3 with base W4. The torque speed plane of an SRM drive can be divided into three regions: constant torque region, constant power region, and constant power speed region. Torque speed characteristics. Region 1. The constant torque limit region is the region below the base speed Wf, which is the lowest possible speed for the rotor. For the small back EMF in this region, the current can be set at any desired level by means of regulators such as hysteresis control or voltage PWM control. Torque speed characteristic. Region 3. In this region, the Q upper limit is reached when it occupies half the electrical cycle. The torque in this region is governed by the natural characteristic falling off as 1 by W square. Power losses. Stator copper losses, core losses, SRM drive system, and position sensor. Commonly used position sensors are phototransistors and photodiodes, Hall element, magnetic sensors, pulse encoder, variable differential transformers. Power converters for SRM. Since the torque in SRM drives is independent of the excitation current polarity, the SRM drives require only one power switch per phase winding. For example, a symmetric bridge converter. See dump converter. Application: flame-proof drive system for potentially explosive atmosphere. Washing machine. Environmentally friendly air conditioning system for passenger trains. Servo system for advanced technology weighing machines. Phase inductance and current ideal waveform. To develop positive torque, the current in the phase of SRM must be synchronized to the rotor position. The following figure shows the ideal waveform phase in a 6x4 SRM. Turn on and turn off angles refer to the rotor position where the converter power switch is turned on and turned off respectively. Thank you.